Perfect. So this is a little bit about me before jumping into the main topic. So my name is Guglielmo Iozzia, and since almost 4 years now, I'm part of Merck organization, and where I basically, for the first 3 years I joined this organization, I worked mostly on implementing and delivering machine learning AI systems in pharma manufacturing space. But lately, in May this year, I moved to a different team, still working in manufacturing, but also shifting my work on the lab, not only so in the manufacturing space. And the scope is a little bit different in this new team. So we do also research, not just working on real life systems. So it's something in between research and implementation of systems, so in the pharma biotech space. I'm coming from similar experience in other industry, in Optum and IBM, before joining Merck, or MSD, is the name of the company if you're based in outside North America. And I'm based in Dublin, Ireland, but literally working with projects in different regions and different time zone. So the team is spread across 5 different locations across the globe. You can see here also some snapshot of some few papers to which I did my modest contribution on implementing the open source version of the system, mostly in computer vision, as a majority of my experience in with machine learning, deep learning is in computer vision, but working on projects on other spaces. And for 2023, from now on, 2023, I expect to have more engagement into scientific machine learning space. Can move to the next slide then. So the agenda for today, so this tutorial is split into 3 parts. The first part, which will be pretty fast, about the importance of using synthetic data, why this is becoming a best practice, a common best practice across multiple projects that do particular deep learning. Then there is the core part of this tutorial, which is basically I'm going to present a real life successful use case of using synthetic images and using deep generative models in the pharma manufacturing. The purpose of this part, which I believe is the most important of this tutorial, is that coming from other experience as speaker to previous edition of the ODSC in Europe, and also lately I've been interviewing a lot of candidates because we had some open position that now we filled. And what I notice is also collecting the questions that people that get in touch with me after these talks and others, is that there is sometimes a gap in terms of understanding what is the how it is working on in the industry. Majority of people coming from a career in academia, or students that try to jump into a new job, etc. And they're very good in terms of having the basics about deep learning, machine learning, data in general, but there is a gap of understanding how really it works when you have to work on some environment which is highly regulated, somewhat conservative, and which challenges you really have with data before jumping into the algorithms, how to deal with business, things like this. So I believe this part will be important if you want to understand more about this particular industry, or if you're moving for the first time outside academia. And there will be a lot of challenges. You will see not just technical challenges, and on top of these challenges, we managed to have several successful initiatives with machine learning and deep learning. The last part will be more hands-on. I prepared 2 collab notebooks to show a couple of examples on how to start with implementing deep generative models using some images that are similar to what we have in manufacturing, which are quite challenging images. Of course, you can understand I cannot show real production images for the hands-on part, so I try to figure out to get some other data set that could be realistic enough for this presentation, so that you can start by yourself. And at the end of each tutorial, there will be some exercises for you to try to improve things. So the goal this time is to make you in a condition to understand how to start with deep generative models, the basic behind this, doing things in Python. We focus in Keras and TensorFlow because all of the systems we have are in this framework, but the same concept basically apply if you do want to do things with a different framework such as PyTorch or MXNet or others. Okay. So we basically, what is this new paradigm that we are observing in the last couple of years and becoming sort of best practice? So you know better than me that if you're here today, you're following the evolution of algorithms for machine learning and deep learning, in particular in computer vision. You're seeing a lot of effort from academia. There are hundreds of papers released every week. But you also probably have noticed that majority of these papers focus on the algorithm part, and they start with some prepared data sets. So the effort of the paper is understanding how to achieve a given computer vision task with a novel algorithm or improving a previous algorithm. But there is very little effort about from the academia about understanding how I could get the data, I could get quality data to achieve my goals. So this means that when you go to the industry, you will face challenges related to the data because basically you have sometimes you have labeled data for some supervised or semi-supervised tasks, but these labels are not reliable because that's a very time-consuming and critical effort when you want to prepare the dataset for training and testing your models. Another situation could be that typically, and this has been something that me and my teams have faced multiple times, we don't want to reinvent the wheel when we start a new initiative, a new project. So we try to understand if some existing paper could be adapted to that particular task. And we found that we are in a condition to replicate the result of the paper with the data shared by the authors. But then if you try to generalize moving the same algorithm to a different domain, that basically most time that doesn't work at all. And last but not least, and you're being for sure in this condition, probably you don't have the data you need, or if you have data, they are not quality data that you really need for your task. So the new paradigm is to use some deep generative models to generate synthetic data to enhance your data set for training models for other computer vision tasks such as multi-classification, object detection, object localization, depth estimation, whatever you have in mind. So that's the purpose of these new paradigms. And if you move down a couple of slides, basically you can see that this is something that really has a market as well. So there are, I can count at the moment more than 50 startups that provide services to generate synthetic data or generate synthetic data for you. And if you can move a few slides further, there should be some examples about synthetic data. Next one, probably. Yeah, oh, no, just next one. Yeah, this is basically, it's important for the conversation we're going to have. So when we talk about synthetic data in terms of visual content, so images, which is the main topic of this talk, or videos as well, there are three things that you have to check to assess the quality of the generated image. So that one is fidelity, of course, that should match what you have to expect from real images. There is diversity, because you want to cover a broader range of situations, including, if possible, also outliers in your data set when enhancing it with training data. And of course, this has to generalize as much as possible to multiple domains. The idea we had for this use case I'm going to present is that basically people are using deep generative models to generate deep fakes. All the images you see in this slide are fakes. You can try yourself going to one of these websites. There are many more anyway, but these are images that belong to more general knowledge domain. So you don't need a specific preparation to understand what is this picture, how a human face is made, or a landscape, or some cartoon characters, manga characters, or others. But what about trying to do this not just for fun, not just for some not good intent to generate deep fakes, but applying this in some more challenging industries, such as, for example, pharma manufacturing, or manufacturing in general, but pharma manufacturing add extra challenge to this. So we can move to the next slide, please. So as I mentioned, there are multiple startups that providing generation of images that I try to categorize myself these startups, these companies, and basically they focus mostly on three main categories, which are image generation for the automotive sector, for aerial satellite imagery, or for retail. You see some example here. These images are all fakes generated by one of these system of these companies. So you can see, if I ask everyone in the audience today what you see in these images, everyone can provide the right answer. Say, oh, the first picture on top, there is an image of a road with middle heavy traffic. There is an aerial picture of a city street, a picture of some snacks, different flavors of the same snacks, things like this. But there are some companies that move further as well. If you can just switch to the next image. There are some companies such as NVIDIA, for example, that is shifting this effort on providing services to generate synthetic images to the manufacturing. There are a couple of examples there where basically the idea is to create some sort of digital twin of the production environment where you can do experimentation without breaking things, and then having a digital replica of the real world, and then moving things to the real world only when you're sure that you minimize the error of what you're trying to do. And this the same we'll try to do also in pharma manufacturing, but there are extra challenges there because, as you can see anyway, the manufacturing side is challenging if compared with the other images. But anyway, all the items you see in those two samples on the bottom right are things that everyone can easily understand what is shown in the picture. Let's see how it really is working with images, computer vision in the pharma manufacturing space on pharma in general. If we move to the next slide, next one. Yeah, there is a look at this picture. So if you're not working in pharma, so this image basically means nothing to you. So it's quite impossible to understand what is really represented there. So when I did other talks about this topic, I asked people in the audience to tell me what they see in these images. Of course, I heard about all the different opinions, but no one could catch up what is really there. So one question I have for you is this one. So if I tell you that this is a picture of a pre-filled syringe with one of our top vaccine, would you probably believe that I'm drunk? Because it's really hard to see where the syringe is over there. But this is just an example of which kind of images you have to expect to work with if you work in general manufacturing, in pharma manufacturing. If you move then to the lab, you have other images generated, for example, by electron microscopes, other tools which are equipped with cameras when basically you can check things, for example, within something within a bioreactor, things like this, and you will see a more challenging images. This is a situation which is not more challenging, but definitely is challenging as well. So moving to the next slide, we'll have the answer to the question, what is here? So the item you were seeing in the previous slide is exactly a syringe, but a pre-filled syringe. So these syringes are packaged with the vaccine inside, and they are shipped as they are for with the liquid inside to be used when they reach the patients at the end. So the use case I'm going to present today, just to give you a broad picture of the system, and then we are going to the specific of the models that we use for the synthetic images and for the multi-classification. So we have a demand to implement some system to provide some advanced analytics and machine learning, deep learning based capabilities to visual inspectors in our manufacturing site. The reason for this system was that the people working at the site, at the shop floor, were coming with an experience of more than a decade, observing that for some top products, we had a high rejection rate of products, and that wasn't the bad news. Bad news was that the majority of those rejected products were really good products. So it means that typically you shape your production on the demand from the patients, and it means that because you have to discard good products from your production, there was a chance that risk that some patient couldn't receive the medicament in time. So we implemented this solution as is a broader solution, not going to delve into more details about it. But basically, the aim was to inspect different products that could be shipped within syringes or vials or other containers in the next releases, and understand provide some insight to the investigators to understand how to reduce the rejection rate for this, in particular the false positives for this. Moving to the next slide, I could explain the main reason why we are observing before this system is a high rejection rate. So typically, this is a requirement to inspect any single unit you want to ship to the market. Is a requirement from the FDA or similar entities in different regions, which means that any single unit you want to ship should be visually inspected with strict requirements about the presence or not of particulate within the liquid area. There is no specific prescription from the FDA on how you could do the visual inspection. So traditionally it has been done manually. Don't know if there is someone that still doing this. In the past years, there was the introduction of automated inspection machine, such as the one you see on the center of this slide from one of our vendors. And that means that when the packaging completes, in this case, syringes flow through these inspection machines, and they are inspected. There are multiple cameras that catch up the syringes from different angles. These machines are based on some heuristics, some rules to which they, from the images, can determine if some product has some defect or not. As I mentioned, the requirement from the FDA is strict about the presence of particulate or not, but with our system and what people did before the system, we want to move further to address different kind of defects, also at the container level, but if we narrow the scope at product level, not just the presence of particulate, but also categorize the particulate observed over there, if any. So not just saying in this syringe there is some particle, but which kind of particle? Let's say it's a piece of fiber, it's a piece of glass, is a hair, is something else, whatever, because the process to produce this is quite complex and long, but things could happen. And then through the system, basically you want to fix the prediction from these machines and provide in a near real time recommendation to the investigators, or at least have an holistic view to where they quickly get insight of what's going wrong some way at inspection time, at production time, of anything else into the pipeline, and go back to, let's say, retuning machine, calibrating cameras or others, or going back to the upstream of the production line. Can move to the next slide. Yeah. Yeah, so here I put also some labels to the previous images, so you can have an idea what you're seeing into that images. So you can see the different part of this range. So these images are quite hard to understand because, as I mentioned, these inspection machines have multiple cameras. We don't use all of the cameras for a specific task of defect detection, classification, because we are basically following the history, the experience of the SMEs that tell us which cameras to use to address a particular class of defects. In this case, we are using this single camera for the multi-classification problem we were going to address, and what you see here is a portion of the raw image. There is a lot of noise here, so we went through pre-processing these images and just identifying the regions of interest and also doing some other transformation. The region of interest are two basically here. The product area, where basically you can find the liquid, the vaccine for one of the 3 products in scope for this task, and the stopper area, because majority of the defect you can see there is also, which is not particulate, could happen into the stopper area. So we are going to pre-processing these images, discard other areas, and at the end we clean up these images to have a single model for 3 different products within the same line. So if you ask me which product is represented here on the next images that I'm going to present as a pre-process, really, I don't know which one it is, because the model is a single model for 3 different products. So this system went to production for the first time in September 2020. Everything was fine up to March 2021. Then the machine learning team started hitting a wall, because we are onboarding a new manufacturing site in North America, and we basically have a new use case, including these images. After understanding the problem, which kind of defect we have to address for this particular task, we start to receive production images into our cloud platform. And we realized that some categories of defects were literally underrepresented if compared with others into the dataset. So no chance to exclude them from the training, because they represent rare events, rare defects, but really important for the business to take the decision for the SMEs as well. So we have to figure out some way to anyway train the model, including those defects. We tried different strategies before jumping into the deep generative model field, and they didn't work, so we tried also traditional data augmentation techniques. We asked the SMEs to run some test batches to be inspected with fake defects. Let's say they start to crack some syringe, damaging some stopper, putting some fiber inside. But unfortunately, those images at the end were unrealistic. So when you see the real production images with these defects, that should be some way in some other slide across this presentation, you will see that are typically really small, and that's really we couldn't use them. So at the end of this, we decided to move to a different strategy. We could move to the next slide. Yes, let's pause. This is important. So yeah, that's you can move to the next slide with the first chart. So when typically we have you have some problem, a classification problem in deep learning for computer vision, but in general also for machine learning, you expect to have some data set of images or other data you need, and then you have to decide, okay, what is the how much data is enough so that myself or the team is in a condition to train that particular model. Typically, what people tend to do is that the more data I have, the better. But that's not the case. So basically, what the real question to answer is that, do you have good data, and can I reach a given performance of the model with the data I have? So one exercise that we start doing after we start this work with generative model, we did for the first time post-mortem, is that how do we know that we have enough data to train the model and then ship this to production, because the performance are good enough to tackle that particular task. If you move to the next slide, I will show an example of this technique, which is called sample size determination. So basically, in this case, we did an exercise post-mortem, as I mentioned. For this particular multi-classification tasks, we had in total 4,588 images. This is just for the training dataset. We already carved out all the images for testing. We try to run this experiment to understand, to have some sort of estimate of the prediction of a given model with these images. And so we create a subset of the training set, 10%, 25%, 50, and 75% in this case, and of course the total of them, to have an estimate of try to predict the performance of the model with different sides of the dataset. So the estimation when using the full dataset for training, looking at this chart, was around 90.8%, which was good. It was overall the KPI for this particular model, and at the end was really close to the real performance of the model with the same set, which was 90.4%, which was a quite accurate estimate. But one information you can see from this chart is that if you look at the estimate of the accuracy of the model, the overall accuracy in this case, with 75% of the images, which is 1,100 images less around that the full data set, you can see that the delta in the accuracy is minimal. So we are still over 90%. So it means that in a different condition where we have 3,400 images rather than 4,600 images, we could anyway ship a model with acceptable performance for our problem. And that's a case where really sometimes you probably say, okay, that's fine. I don't need to ask for more images. And most of all, I don't need to ask to people to label more images, because that's one part of the process and for machine learning and deep learning, which is quite expensive because you need people time. We have, as part of the platform, automated labeling, job creation, and sharing across the users. But anyway, you need time for people to work on this. And of course, if you recall the image I showed you before, I'm going to show others, that's require a specific knowledge to label these images, so you cannot rely on external labelers for this. So these are the things, some of the things you have to think about when you work in a real life project in the industry, because you have to think about time and costs, but time also is cost as well. So that's, you have constraints, and you have to justify to the business, the stakeholders and your sponsors, how much you're spending and why mostly you're spending so much. If we move to the next slide, there is another example of this exercise of sample size determination, where basically this is narrowing the scope to a single defect category, which was underrepresented before generating new images. You can see for training, we had only 120 images. We had all the other 30 for testing. Running the same exercise, and this time basically you can see that there is a bigger delta between the estimated accuracy, which was an optimistic 90.7%, and the real accuracy for this category that was 81.1%. So that's there was a discrepancy. So definitely we needed more images to train the model, including this category as well, and same for other three for the same use case. So we could jump back now to the main topic on how we next. You can go to the next slide. Yeah, this one. So here I put some examples. No, sorry, the next one. The one, yeah, this is with the defect types. So basically in this slide, I put all the categories of defects that we need to address for this particular task. On the left, there is an image of a good product that has been anyway accepted properly by the inspection machine. I put that just as a reference with the other images. And you can see here another challenge. So if you look at all these images, you see that the defects there are quite small, and also there are multiple patterns about the bubbles inside the liquid area. So these bubbles are there because when the syringes pass through the inspection machine, they pass pretty fast. They rotate around their vertical axis, and that's basically the liquid shakes inside and creates bubbles, which is not an issue because that's just due to the passage of the syringes there. But sometimes bubbles are so small that these inspection machines are fooled easily. So basically they think that a small bubble is a particle, and so that particular unit of product is rejected, and regulation prevents you to put it back to move further on the supply chain. So with this system, we are trying to address this to reduce the rejection rate and other insights to the users. And you can see that because there are so many patterns into the liquid area, is one strategy that wouldn't work as well to have new images is just to try to patch images of accepted products, which we have millions, with some defects, because anyway, there are some multiple patterns that would be impossible to create realistic images. In this slide, you see there are some images marked in red. Those were the categories that were underrepresented, for which we weren't in a condition to train a multi-classification model for this use case. Also for liquid in ribs was something in between, but after running some size experimentation, we realized that we have a good number and quality images for this category. So if we move to next slide, we'll see which kind of categories. Oh, this is a sort of question that we for which that typically people ask when approaching me about this topic, and I put the answers at the end of this slide. And so if we can move to the next slide, we will, yeah, this one. So what we did, the idea was moving to deep generative models to generate the synthetic images for the categories we need. Before moving to that, we try to a different approach. Say, let's try to have some model agnostic meta learning approach that we replicate the result of a paper from OpenAI successfully, but then moving to our specific topic, it didn't work. It didn't generalize really. I'm not going to spend details on that because it's out of scope for this talk. I will focus on the other two strategies we put in place by using, so we split people working on two different options, a variational autoencoder and a generative adversarial network approach. We initially have the assumption that was wrong, that these two approaches were mutually exclusive. So we said one of these approach will probably work and the other one not. But at the end, we'll see how this ended up. So just to have everyone in the same page, so you're not familiar with this concept of in deep learning, so in generative models, a variational autoencoder is an architecture where you have upstream neural network that takes, in this case, images and input, and then does some sort of dimensionality reduction, and basically maps this image in a latent space which has a dimension which is lower than the original images. Then downstream there is another neural network called decoder, which basically gets some vector from the latent space and tries to reconstruct the original image. Someone could think that's a big deal with this, but this is really important. You will see how you could use this network lately. We didn't try an approach with a vanilla autoencoder because that's not suitable for a production project. But basically, we use a variational autoencoder where the latent space is a distribution of values, not single input. And you will see in 1 minute on our model and the code examples I prepared for the last part of this tutorial. Then the other option, the GAN, basically is an architecture where, again, you have two neural networks train each other. That's why it's called adversarial. One is called generator. It's trained by using real images after injecting some noise to them, and then basically it's trained to generate deep fake images. While the discriminator, the other network in this architecture, is trained by using both real images and fake images generated by the generator, and so it's trained to try to understand if any image, classify if an image is real or it's fake. The equilibrium of this network is reached when basically the discriminator isn't able anymore to understand if an input image is real or fake, and in that case, basically you discard it and just use the generator to generate new images. So let's see how the approach went for all these two strategies, starting from the variational autoencoder, and we move to the next slide. Yeah, so basically what we did was typically a variational autoencoder approach is unsupervised, but before we start the destination multi-classification task, we didn't know yet before doing EDA that we didn't have enough data images for some particular categories. So the labels labeled all the existing images, and when we start this approach, we have anyway labeled for any category represented or unrepresented. So we use also the labels of these images to get some insight, understand how to generate synthetic images from this approach. So we train our architecture, and the latent space was very small in this case. We reduced to just 2 dimensions. This also, other than making this problem simpler, also makes easier to visualize the latent space, and the team could start to understand where which areas of the latent space pick up to generate some models. So some images, some new images. So what after the training completed, basically we took the test data set and use this to use the encoder to encode this into the latent space. And you can see here, this is an example, one of the test sets we used. There are some, there are different colors that represent the test images belonging to different categories. As you can see, there is an area where there are multiple points overlapping each other from multiple categories overlapping each other. So definitely we cannot use that area, because if you move in that part of the latent space, you definitely get some images that don't make sense at all. But you can see there are on the top 2 green distinct groups of points, another one on the bottom right with a yellow point. So we are discarding this area with the yellow points because those refer to the test images belonging to accepted products. So we have millions for them, so definitely we don't need that anyway. They are not part of the training of the model. The model is trained using just images of defective products. So what you can do in this case, what the team did was to navigate an interval of the area around those part of the latent space where you see there's distinct categories points, and moving across the 2 of them, you can move the animation to the next one and see what we discover in this case. So basically this area on the top left, moving on that portion region of the latent space, the decoding process start to generate some meaningful images of incorrect stopper, which was one of the categories that we basically were underrepresented. While doing the same exercise, decoding some point in the latent space in the other green region, this decoding process start to generate meaningful images of inverted stopper defects. So this, you can see the resolution, of course, as expected, is lower than the original images, but that was not an issue because we put a super resolution algorithm downstream of this process, so to match the quality and the resolution of the original production preprocessed images. So far, if you recall the slide with the underrepresented categories, we partially solved the problem because in this case we were able to generate meaningful synthetic images of 2 out of 4 categories of those underrepresented. Let's see in the next slide how things were going in parallel with the team working on the generative adversarial network approach. We can move to the next slide, where there are some samples here. Yeah, so basically all the images you see in this picture are deep fakes of defected prefilled syringes. Of course, all the image we generate are similar to those after preprocessing. We are not generating noise or region or that are not of interest of the raw images. This experiment, of course, was more complex. It requires a more computational power because, of course, GANs are more power hungry when you need to train them with these wide data sets. So that basically at the end of the process, so I'm cutting short all the details about how we reach the final architecture. By the way, for both this use case and variational autoencoder, we are talking about a convolutional approach. After training for a greater number if compared to the variational autoencoder of epochs, the final architecture we found, then the generators start to generate realistic images with the exact same resolution and quality of the original images of molding defects and dirty stopper defects. So basically, those are the other two categories that we couldn't manage to generate images using the Y approach. The team then want to move forward and say, what if we take this architecture and let's say train with a larger number of epochs, but anyway, to reach this result, we have to train for 5,000 epochs. So if we moving the training for a larger number of epochs, basically the performance of the GAN were still good. We're still seeing generation of images for these defects, and also start to generate some images of liquid in ribs defects, but that at the end we didn't use because we realized that for that category we were good. So of course we couldn't use the totality of the images generated with this approach, so we have to discard at least 30% of the generated images. The main reason is not that those images weren't realistic, were too much realistic. So because if you remember what was the goal of this exercise, is to produce synthetic images to balance a data set for training. So we want to generate images that for training purposes only present a single defect for each image. Of course, in production, you will see incoming images of products with multiple defects, but that's fine at different times. So the model can final model can tackle that for defect detection, but at training time we need to teach the model to recognize a specific category at the time, and so there should be a single label for each training image, and that's why we could use majority of those images. Also, there were some related to accepted products, but less than those generated with the variation autoencoder approach. Moving to the next slide, there are some more numbers and details about these two approaches. So as I mentioned before, we did a wrong assumption, thinking that these two approaches were mutually exclusive, which they're not so, because we have to use both to generate all the images we need for all the categories we need. The variational autoencoder network, the final one, was better at creating images where basically those category of defects are spread along one of the two regions of interest, the region of the stoppers, in particular the ribs level, while the GANs was good at creating images where you have localized defects, such as, for example, some piece of dirty into the stopper or similar, or same for those images in liquid in ribs. Sometimes you have small drops of liquid within the ribs, and those are the kind of images that could be generated training for more than 5,000 epochs for the GAN. While for the variational autoencoder, the final training was of just 50 epochs with the final architecture. Both approach for this use case was good in diversity, but don't count on this for other problems. So each use case is different. So if you have other kind of images, probably that wouldn't be the case. So you have to try multiple architecture, or probably you will have a single architecture which is good at the diversity. The variational autoencoder was better in terms of generalization. Well, of course, as you saw those images, the quality of the GAN was better, really matching the one of the real images. As I mentioned, the training was quite expensive for the GAN in particular, because we have to train in some instances equipped with GPUs. If you don't have GPUs at all, the training could last for around 14 hours, so that is too much. So with GPUs it's just few hours, while it's pretty fast on an instance with just multiple CPUs and enough RAM for the variational autoencoder. There are some metrics that you typically use to assess the quality of the generated images. For example, if you look just, again, you have plenty of metrics, but of course, while the team was assessing these metrics, what we did was to basically take these generated images, put into our cloud system, create some labeling jobs for the SMEs mixing real images and synthetic images, and asking them to label these new batches of images. So they didn't have idea that there were also synthetic images and real images. So they start labeling, so they are the domain knowledge expert. They completed the labeling. There were 5 or 6 people, and they reached consensus on labeling the synthetic images with a proper label. At the end of this exercise, we told them, so you were labeling also fake images, and so they gave us clearance to use these images to train the multi-classification model. What happened when we finished this? So we prepared the pipeline to train the multi-classification model by mixing the dataset with images. Production restarted. There was a stop for maintenance, so that's the reason that we couldn't expect more batches of syringes to be inspected, and so receiving new images possibly for these new categories. So at the end, what we did was to accelerate things to ship the first release of this model to use only production images, because we were lucky that we have some batches where there was a high rate of real product having a molding defect or other defects that were underrepresented, but that was just the first release of the model. So we, in the future releases, we basically use a mix of images, real and synthetic, to train the model. And in the next slide, you see the result that we achieved for the model we have in production for this use case. So you can see here, basically, we compare the performance that I confirm because these models are monitored in production. So you can see that by using real data only for training, and then using a mix of real and synthetic data just for those categories underrepresented, we are losing something in terms of performance, around 1% in for the overall F1 score and composite score. But we observe that we are gaining in terms of generalization, because incoming images, so the generated images present also some variety in pattern in terms of bubbles or other elements of the images of the defects themselves that weren't observed before in production, but now monitoring also the data, looking for outliers of drift on incoming images, we observed that the performance of the model in production didn't have significant deterioration. So that was good, and this is the way now for each pipeline. So this wasn't just a once in a lifetime exercise. Once we understood how to tackle these problems, we're having this as part of the overall automated pipeline to train models, so generate synthetic images and then put them into the pipeline to train the model and just testing on the real data. As I mentioned before, depending on a use case, you will have to work on different generative architecture. So in this case, where everything worked with using 2 distinct architectures, sometimes you could have just one. Sometimes some of this approach doesn't work. So sometimes VEA doesn't work, or the GAN doesn't generalize enough. So it depends on the specific use case, on the content of your images, and the quality of the input data set that you use to train these generative models. We can move to the next slide. So I didn't mention so far anything about the tech stack used, because I want to give you a full overview of a real project, and I mentioned some challenges that are related to costs. So typically, by default, when we start a new project, we don't have immediately availability of instances with GPUs. We have powerful instances with multiple CPUs, a lot of RAM, but you have to justify the usage, and then you get clearance to use some instance with GPUs. Anyway, you have to look a lot about performance of your model, trying to shrink the performance of the model at training time, but also difference time. So trying to do some optimization, some quantization as much as possible, understand if the architecture you're choosing for a given model is overkill or is the right architecture. So there are a lot of consideration you have to do, and often you cannot use the state of the art for some particular models. So I didn't mention anything about using some diffusion-based generative models, because when we started this work for the first time was March 2021. We weren't confident to use a model based on diffusion to generate these images, and also the computational power to train that model is quite expensive. So there was we have to move faster to ship this model and others to production, because that was one line of products that was giving the greater problems in terms of generating false positives. So we have to address this and speed up the work of the SMEs to fix things and move to some regime where you have a very low rejection rate for these products. So we did, this system is implemented on the cloud. AWS is our partner in this case. And the tech stack is quite common. So we do things mostly in Python, Keras and TensorFlow. So we use typically Keras high-level APIs for training or more standard tasks, but some things we do using pure TensorFlow. We integrated Keras Tuner to do automated hyperparameter tuning of the models, OpenCV only for the preprocessing part of the images, and we use Amazon SageMaker for development and of course for serving the model. And we integrated MLflow within SageMaker because SageMaker experiment doesn't have the feature we required for our experiment tracking, which is an important part of each machine learning, deep learning project. And also we use the MLflow registry to keep track not only of the experiment, but also of the serialized models. And we use this then to, when we pick up a candidate to move to the next stage to test pre-production or production, we have our automated pipelines to pick up things and deploy to SageMaker endpoints from there. So this is more or less the tech stack used. And of course, there are other services in AWS that you use for data engineering or other stuff, because of course, we use different data, not just images. We need to create a context to these images, and we use data of different nature as well. So in the next slide, there are the answers to some questions that typically people ask in terms of synthetic data. And the first question, and I try to provide some answer here. The first thing is about if synthetic data that you can generate through one deep generative model architecture cover outliers that happen in the real world data. Unfortunately, this doesn't happen unless you have already outliers into the input set, which was the case for us in one of the training set for some categories for the variational autoencoder, but doesn't mean that you have this. So as part of our automated pipelines, we have also a monitoring system to catch up outliers or novel patterns for these images, and then try to understand if we could reuse or introduce this to retrain the deep generative models. The quality of the synthetic data. So this is really correlated to the quality of the input data. So if you put garbage in, you will have garbage out. So that's, I think, should be clear. User acceptance for synthetic data, definitely that's not a challenge at all, because what is important in real life project is that if you show for not just for this particular task, but in general, what is the business value you could realize with a given solution, users will be open to this and other. So we didn't have resistance at all to use this data, because they understood that we could move to production that particular model and block their work if we didn't have enough data to train the model. So in terms of time of effort needed for this. So if you in general have a platform where you automate things as much as possible, that's the effort compared with more standard deep learning tasks is not too much. Of course, you will need these things doesn't come for free in terms of getting the right architecture for the problem. But anyway, if you have the people with the right deep learning skills and people with understanding of the problem and the right level of automation, that is not a big challenge at the end. In terms of accuracy of the output of these synthetic data generation models, so that depends not only on the quality of the data, but how much understanding of the problem you have. So in our case, basically, we went through few months of interacting with the SMEs. So that's clear to have a continuous communication with the domain knowledge expert. So we start thinking how they think. So they have years of experience on this matter, and we have to transfer this knowledge from them to ourselves, to our generative models to produce as much realistic data as possible. Could move to the next slide, which is, of course, this is important. So this today I presented a use case in the pharma manufacturing or using generative models, but that's not the only use case in the pharma industry. We have other use cases in house for other tasks which are not computer vision, and there are some, for example, you already know, in terms of protein folding, for example, molecular optimization. Some other could be just using variational autoencoder to do anomaly detection in time series signals, so using data which have a different nature. Let's say, for example, our electric signals, just to mention something you have in manufacturing, there is a reticular materials discovery or material engineering. There are multiple use cases and tasks of deep generative models that are literally revolutioning this industry, and that's basically is evidence that these things are not just for deep fakes. Unfortunately, when you read the news, you heard just about deep fakes, but these are the things that you could do with deep generative models, and many more to come next, also in other industries. So these things is happening is in a very conservative industry such as pharma, biotech. This could happen in other industries as well. Next slide, I think, is the last one for this part of the presentation before jumping to some code example. So this slide basically is much more, I went to some other event where the audience was much more business oriented and less technical than probably yours. And so there is just one thing that I want to highlight here for you, that it's important for success of not just project using deep generative models, but in general in machine learning, deep learning, or whatever it comes next in AI. It's critical to invest in people. By people, I mean the domain experts. So that's crystal clear. So you can just jump into a new field. You could be the best machine learning engineer or data scientist, but if you don't know anything about the field, that would be critical. So you have to learn a lot about the particular domain knowledge. So work with these people and hope that you have the right domain expert in that particular company or customer you're going to join. Then, of course, machine learning engineers, data scientists, software engineers, because these things have to then be implemented and moved to some platform. Could be the cloud, could be HPC, could be something else on-prem, whatever. And so that's crystal clear. And just to give you a tip, so if you are trying to find your way into this field, please spend a lot of time about data and also focus on a few domain of expertise. So let's say, what is your passion? You would like to work in pharma, you would like to work in healthcare, or like to work in manufacturing, cybersecurity, whatever. Try to become an expert or the general counsel of that field, because that's really some things that can make you successful in your career and make you also more marketable, because that's really makes the difference between a good machine learning engineer or data scientist and less good machine learning engineer or data scientist. So this was the last slide for this part of the presentation. I shared with the with the organizers a couple of notebooks that I want to present myself. So we have to do this in a mixed way. So let's see how this works. By the way, the notebooks will be shared in GitHub next week. Unfortunately, at the moment, I'm in the middle of different things at work and others, so didn't have a chance to wash them up. And I want to add some information at the end about some exercise that you could do yourself to understand more more on there. So don't know if you're in a condition to share the first of the two notebook, which is the one called convolutional. Perfect. Yeah, this is the right one. Okay, so basically what I did here is to prepare a couple of code examples in using Keras and TensorFlow. So once I do a wash up of these notebooks, you can use them by yourself to play with them. So as I mentioned before, now you're seeing a lot of new generative models that also combine visual content and text, not just visual content, that are based on some diffusion algorithm. But it's important, even if you want to tackle this problem, to understand the basic. So in this first notebook, of course, I cannot share the original code and the architecture we used. Cannot use the real images from our production for that, so would be fine for that. But I went to Kaggle and find a public dataset to be used for this exercise, which show the same way the team started to tackle the first experiment with a variational autoencoder. In the second example, you will see how make things more complex, and you will see that there is something overlapping this domain of generative models and other more complex models that combine text and visual context. So all the dependencies to run this are already in Colab. If you run this also in the free tier environment, you have just to install the Kaggle API package. And there are other two option dependencies that I'm using just to generate a GIF of the 20 generated images at training time. But if you don't need this, you can skip this part of installation, just install the Kaggle API. The TensorFlow version that could be used, I think this is compatible with TensorFlow 2.6 or later. It's up to you. I run the same notebooks on Apple Silicon M1, so you can replicate the same over there. So I'll put some instruction into the GitHub repo as soon as I wash up this. So if you want to run this locally, you can do it seamlessly. So this is basically the first one is about a variational autoencoder. It's a quite simple implementation, and you see this. The first part is about the data preparation. If you scroll a little bit up, yep. So this is the way. Probably, if you're not familiar, sorry, scroll down. My bad. It was yeah, this is the part where if you identify some data set in Kaggle that you want to use for your personal notebooks on Colab or different environment, you can use the Kaggle APIs. You need basically to generate your Kaggle token into through the Kaggle UI. So you go in the settings section, and there is a button to create this token. It's a JSON file that is downloaded locally, and then you need, in this case, to upload to Colab. Once you have this, you can do multiple things. In this case, I'm just using dataset, so I already know which is the ID of the dataset I want to use, and you can see over there. And so use the Kaggle dataset download command to pick up this dataset and upload it automatically into your Colab virtual machine. And then the commands that follow is just to unpack this dataset. So you can scroll down a little bit. And from there, basically start creating the training and test dataset. And there should be also a sample of the images. If you can scroll a little bit further. Yeah, so this is a sample of the images in this dataset. A quick explanation of this data. So this basically is a data set coming from some manufacturing productions or real images, which represent some good or defected units of submerged pump impellers, which are in this case are covered, and what you see in this picture is the top of this element. So if you want to browse in through Google to understand what these elements are, but basically it's important to understand for this presentation that you can see all the pictures are being taken by the people that prepared the dataset with a camera that catch the top of these units. And I didn't use the images of good products for this presentation, the notebook and the other one, just taking the images of defective products. If you look at the way they are structured, these images are already split into training and test set. But there are just two categories. There is good products and defective products. There is no fine grade categorization of the defects. So looking at these 10 samples you see in this page, you can see that there are different defects, but anyway, the label is the same. So that's not a problem for generating these images. Of course, as an exercise, you could probably do some EDA and categorize these images into different defects. Some of them present holes in different part of the units. Some others have completely messed up borders, things like this. You see some example here. But anyway, we just want our variational autoencoder to generate, if possible, realistic images of these defected units. These images have a resolution 300 for 300 pixels with 3 channels. Do some standard data preparation to preprocess them before using them for the model. And if you scroll down a little bit, we could start see the code that basically implements the architecture for this model. So as I mentioned, not using in this case a vanilla autoencoder, is a variational autoencoder. The difference is that without using any math formula to explain this, is that when you train the model, you have the encoder network that takes images in this case as input, and the result of this process into the latent space is not a single vector, but are 2 vectors. So basically, each vector is represent the mean and the variance of a Gaussian. So it's not a single point. You can think about not a single point into the latent space, but it's a distribution for each input image. From there, basically, a vector is sampled starting from the latent space, and that is the input for the decoder at training time, which tries to reproduce the original image. Not only that, but also calculate so what is the error and the difference between this image and the original one. And of course, this is back propagated, and the parameters of the model are updated accordingly, same as for other training in other deep learning tasks for other deep learning architecture. So the implementation of this process is quite simple. So this network, I basically using the TensorFlow Keras sequential API and a very simple convolutional network implementation for the encoder and the decoder. So basically the decoder has the same architecture as but for the encoder, but is of course inverted. So you see the first the latest layer that is similar to the first layer of the encoder. And what you have to implement in this, if you scroll a little bit down, is basically the implementation of the encoder. The decoder doesn't have any difference for any other convolutional neural network. What is different is that you have to implement the function to basically generate, produce the 2 output vector of the encoder, and then the function to sample the vector which is the input for the decoder, and of course you have to override the training step because you want to add this to calculate the loss for at training time. So you can see here there is the implementation. Likely, so this is more difficult to explain than to implement, because TensorFlow provides all the APIs to implement this, and also some more complex things that you will see in the next notebook. So if you scroll down a little bit, Yeah, here there is the last part of the explanation of this implementation, or in general of variational autoencoder. So what is the goal at training time? At training time, really, fortunately here I have to use one mathematical formula, but it's also easy to explain in other terms. So basically the goal of the training is to maximize as much as possible this which is called the elbow evidence lower bound, which is this key value that basically give you some hints about the quality of your model at training time. So, and this basically is, if you look at the last part of the, 10 minutes left, so we need to hurry fast. So basically, the goal here is to try to maximize the Kullback-Leibler divergence between the posterior and the prior for the generated images at the decoder part, and at the same time reduce reduce the divergence, but at the same time maximizing the likelihood of the generated image. So we can, and this need to be implemented as part of the loss calculation for the model, which is in the cell below this one. If you scroll down a little bit, here, this is the implementation. Cannot go through details of this, but scrolling a little bit down when we train the model, we can see some generated images. If you scroll down a bit, there should be an animated GIF that shows the evolution of the generated images across 50 epochs. Is a little bit down. As soon as you can see something moving, hey, this one. So basically, this is a GIF that is generated to show how the generated images to test how the process is going, the training is going across multiple epochs. As you can see, these images start to look like realistic, but that's not yet a good situation because there is no much diversity in terms of defects. So if you can move to the next notebook, I will quickly show what is the result moving to a more complex architecture and moving the latent space from just 2 dimension to 16. So this is an exercise you could do also for this use case. And the other architecture I prepared in the other notebook is related to the VQ VAE. So if you have you can show the other one. Yeah, so basically this is another architecture that probably you have heard about this, vector quantized VAE, because this is behind the scene also in some latest generation generative models which combine text and images such as DALL-E. So this is basically the difference here is that you need to put an extra layer which is called a vector quantizer between the encoder and the decoder. The implementation then is the same as for a traditional variational autoencoder, and this also flattens the input into the latent space, but for the channels, and generate also the so-called code books, which are the discrete representation to the particular vector in the latent space. Scrolling down a little bit, you can see that this is part of the DALL-E architecture as well. As part of the VQ GAN, you can recognize also where is the variational autoencoder, or better, the VQ VAE. And scroll down more, you can see the result of using this approach. And you'll see that we have more realistic images, in particular in terms of diversity. So the scroll down when you can see some generated images. Training for 25 epochs with this approach. Yeah, here. So you can see that there are also, the quality is still not perfect, but if you look closely at these images, you can see that those particular images where you have small defects, such as small holes, or where there are dents on the border of the impeller, those are exactly replicated by the decoder, and also other features such as lighting, etc. So that is a better approach, and you can then use this and try to understand as an exercise. I will put this in the final notebook, how to generate novel images with this second approach. So I think we have very few minutes for questions, so probably we will need to switch to to that. So let me see if I can see the chat. Yeah.
There's one question in the chat from David Grayson on the channel. Could the speaker describe what better generalization of real and synthetic data training versus real only mean in more detail?
Oh, basically, we run two separate experiments. So, because when we started use case, we didn't have enough images, real images, for all of the categories to train model and reach the required performance. So the training with the real images means that in that case, we use only real images and not synthetic images, because for that use case, at a given point in time after we finish the generative work and every synthetic images, we receive new real images to balance the data set. So we run in parallel experiment with the same model, but using different data sets. In the first release of the model to production, using only production real images. In the later version, we mix real images, production images, with synthetic generated images for those unbalanced categories. And we compare the result and compare also the performance in when we move to production with incoming novel images. That's the difference between those two experiments. I hope it's more clear now.
Okay, and there's a follow-up part. Let's see. It seems part of the difficulty of this approach is that you're starting with anomalies that are very rare in the data set. So a generator trained with that data set should theoretically reproduce a similarly low frequency of those anomalies, which means that in the synthetic data set, you still may have to manually sift through enormous amounts of negative examples to find the anomalies. So was the distribution of data fed to the VAE or GAN models filtered in some way relative to the data being fed to the classifiers? And how did you sample from the synthetic data? Was there any pre-selection process before sending it to the subject matter experts for labeling?
Okay, so for the first part, unfortunately, I cannot share the numbers on how those are being sampled, and was an iterative process anyway, because when we jumped into that particular multi-classification task, we didn't have idea that we wouldn't have enough images for some categories, but the labelers were labeled everything, and we received also other images from previous batches. So before this system went to production, there was no automated ingestions or ingestion of images and metadata. So we have to pick up images of all the batches of products, put this into the cloud as manually, not a part of it, and then we start to get other negative samples from there. So in terms of the selection of the images to submit to the SMEs, that basically, because we have an automated way to create labeling pipelines, where basically, I cannot show you the UI, but I can describe what it is. So you have some search, we implemented a search engine for images, where you, depending on some condition, do some search similar, such as, for example, when you search for images in Google. And then when you have these images, you can select all of them or a subset of them, and automatically create a labeling pipeline. So that was quite easy for us to set up a huge, massive the pipeline of synthetic images to be labeled, covering as much as possible. Of course, we reviewed to include all of the possible patterns generated by the synthetic models, and post-mortem also we had some conversation with the SMEs to basically review other generated images. So that's something that now is part of the the final pipeline for each model. So we have generated images that automatically go into our cloud platform. So they are available in S3, are available through one of the web apps that they use to search images and do some analysis on them. And then we basically, in some cases, we have to refine the models because we found some interesting new patterns. But that's the way we basically did and do to select the images to submit to them for having clearance to train the models.